Watch the previous lecture for section 2 and 3 on chapter 6, right? And I told you that for section 2 and 3 I have covered until slide number 13, right? Let me okay, so in that lecture I've derived this Jacobian matrix. So by now you should know what is a Jacobian matrix. And as you know, Jacobian matrix, it maps joint velocity to spatial velocity. All right, that's the Jacobian matrix. It is a function of robot joint angles, and it's a relationship between the spatial velocity and the joint velocity. Okay, so if you have a 6 degree of freedom robot arm, theta dot consists of theta 1 dot, theta 2 dot, up to theta 6 dot. All right, and theta dot, it is d theta dt. It is the time derivative of theta. And spatial velocity, we have the linear velocity or translational velocity components and the angular velocity components. Okay, all right. And by now you should know how to derive this matrix. So in order to derive the Jacobian matrix, you need R00, which is identity matrix, right? 3 by 3 identity matrix. You need R10 up to Rn minus 1, 0. Okay, in this case, our n is 3, and you are given T10, T21, T32 in the question. So you need to compute R10 and R20. Okay, and you know that you can compute T20 by multiplying these two matrices. You can compute T30 by multiplying T20 and T32. And you need this, right? This is Px, Py, Pz. Remember, this is the position of the end effector, or the third coordinate frame with respect to the base coordinate frame 0. So you need, so in this derivation, this is known as F1, this is F2, and this is F3. And in order to compute the Jacobian matrix, this is del F1 del theta 1, this is del F1 del theta 2, this is del F1 del theta 3. So where do I get that? From this, if you remember, right? And the second row you have to use F2, and similarly third row you have to use F3 to take the derivative over theta 1, theta 2 up to theta n. Okay, so I hope you know that. If you don't know, you have to ask me another time, all right? Or maybe today if you want to interrupt me anytime. Okay, so let's proceed with slide 14. And I don't think I have uploaded this on e-learning. If I have not uploaded this on e-learning, I will do it today. Okay, so for the Puma robot in the configuration shown in figure 3, this is figure 3. If we have all joint angles to be 0, this is how the robot will look like. The Jacobian matrix is given by this. Okay, each row corresponds to a Cartesian degree of freedom, or spatial degree of freedom, right? We know that this corresponds to Vx, and this would correspond to, or this will produce Vy, Vz, and this will produce omega x, and so on. And each column corresponds to a joint. It is the end effector spatial velocity created by unit velocity of the corresponding joint. So I've shown you why this is the case in the previous lecture, right? So in this configuration, motion of joint 1. So if you have joint 1 moving at 1 radian per second, right? Only joint 1. So where is joint 1? This is joint 1, right? This is the axis of motion of joint 1, and this is joint 1. So if you can imagine, joint 1 rotates at 1 radian per second in the z-axis, right? So this is z-axis, positive z, and this is positive z. If we say positive 1 radian per second, it should be this way, right? Clockwise, right? If you look at the bottom towards the arrow, 1 radian per second means a motion like this. All right. If that's the case, that will cause motion in world x and y direction and rotation about the z-axis as given by the first column. All right, so first, joint number 1 corresponds to the first column. Any motion of joint number 2 will affect as given by column 2 and so on. So if we have only motion in joint 1 at 1 radian per second, you can expect the end effector of the Puma robot will have Vx, Vy, and omega z. Okay, so let's look at the figure and see if that's really the case. So from this column, we can see that if theta 1 moves at 1 radian per second, we would have negative 149.09 meter per second in the x direction, positive 411 and 48 meter per second in the y direction. So let's focus on the end effector, right? So if joint 1 moves at 1 radian per second this way, for sure, and the rest of the joint does not move, right? It has 0 radian per second. For sure, this end velocity will not move in z direction. For sure, right? And that's why we have 0 here. And does it move in x and y as given by these values? Let's focus on, let's project it. If we project this point on the x and y plane, so let's look at this point here. So if joint 1 moves at 1 radian per second, we can see the end effector will move in this direction, right? In this direction. And that direction has negative x component and positive y component. All right? Which is correct. Also, the end effector, so if you have a camera on top and you only focus on the end effector's motion, you can see it will rotate it can rotate about z axis, positive z axis, this axis, okay? So indeed, the first column shows we will have a non-zero rotation about the world z axis, okay? So that is how you interpret our Jacobian matrix. So from our Jacobian matrix, we can see what is the effect of individual joints on the spatial velocity. So motion of joints 2 and 3. So this is the effect of joint 2, and this is effect of joint 3. Cause motion in the world's x and z directions and rotations about the y-axis. And of course, if you have the final spatial velocity of the end effector will be a combination of all this, of all the motions of each joint, okay? But if you want to look at or analyze the influence of individual joint, then you have to look at the individual column. All right. So let's move on. So that is the manipulator Jacobian. All right. Up to now, we have covered the Jacobian matrix. So what you have to know up to now is the Jacobian matrix. It maps, or it shows the relationship between joint velocity and the end effector's spatial velocity. Okay. And by looking at individual columns, we can analyze the influence of individual joint on the end effector's spatial velocity. All right. Now let's look at Jacobian condition. So we have discussed how the Jacobian matrix maps joint rates, the angular velocity of every joint, to end effector Cartesian or spatial velocity. But the inverse problem has strong practical use. What joint velocities are needed to achieve a required end effector Cartesian velocity? So which means if I want the end effector to move in a certain way, I want to know what is the required joint velocity. So it's the inverse problem, right? So we can invert the previous equation and write. So if previously we have nu equals to j of theta multiplied theta dot, and from this equation, if I know what is my joint velocity, I can more or less know what is my end effector spatial velocity, right? But what if now I know what is my spatial velocity, right? I want to know how my end effector moves, and I want to know how can I produce that movement by actuating my joint. So I need to invert this equation. So theta dot equals to j inverse of nu. Theta dot equals to j inverse of nu, provided that j is square and non-singular. So j is a matrix, correct? So in this case, j is a square matrix. So I hope you know what is a square matrix, right? Maybe you have learned in your first year or second year mathematics courses. So a square matrix means the number of rows are equivalent to the number of columns. So in this particular example, we have 1, 2, 3, 4, 5, 6 columns. 1, 2, 3, 4, 5, 6 rows. 6 rows, 6 columns. So this is indeed a square matrix. Okay? And in fact, so all the examples that we have seen up to now has a square Jacobian matrix. But there is a possibility that we will have, in this example, sorry. So this is a 3 degree of freedom robot, right? And look at our Jacobian matrix. We have 1, 2, 3 columns. How many rows? 1, 2, 3, 4, 5, 6 rows. So this is a 6 by 3 matrix. This is not a square matrix. So therefore, you cannot do the inverse. You cannot compute the inverse of j. Okay? So in order to... So it depends on your J matrix whether you can perform the inverse or not. And J has to be non-singular as well. So these are the two conditions for us to be able to compute the inverse of J. Number one, it has to be a square matrix. The second condition, it has to be non-singular. So what does that mean, right? So let me try to write it. Let me try to have my canvas as big as possible. Let's double it. 2000, 4000, and 2000. All right, it's big enough. Is it? Oh yes. All right. So this is more or less can be a refresher of what you have learned probably. Where's my pen? Oops. Oh no. Okay, sorry, I need to set it. I need to do some settings here. Because it's inverted. Where is my tablet? Please give me a minute or two. All right. Okay, so what is if you're given a J matrix? Okay, what is the inverse of J? Can you remember? Can someone tell me what is the inverse of J? How do we compute the inverse of matrix J? Say it again. You're breaking. I cannot hear. Not transpose. I cannot recall. Was it transpose? No, it shouldn't be transpose. It should be 1 over determinant of J. Okay. No transpose. Adjoint. Multiply adjoint of J. Okay. So please remember this. You know, you'll never know. In your future interview question, they might ask very fundamental questions like this. Okay, this will test your engineering knowledge. Anyway, so J inverse equals to 1 over determinant of J multiply adjoint of J. So from here, if I give you a condition, right, J inverse can be computed if what? J inverse can be computed if what? If I ask you only to look at this equation. Yes, very good. Very good. So if the determinant of J is non-zero, right? Because if the determinant is 0, 1 over 0 becomes infinity. Okay, good. So, if determinant of J is non-zero, we call J to be non-singular. Let me change it for dramatic effect. Okay, so in mathematics, we call J is a non-singular matrix if the determinant is non-zero. All right, let's get back to the notes. Where are we? Okay, so we are here. we want to compute J inverse, provided we can compute J inverse if it's square matrix and the determinant of J is non-zero, or in other words, J is a non-singular matrix. Okay, so thus in order to achieve a square Jacobian matrix, a robot operating in a task space which has 6 spatial degree of freedom requires a robot with 6 joints. So this statement means if you require the end effector of your robot to have Vx, Vy, Vz, omega x, omega y, omega z, then you need a 6 degree of freedom robot with 6 joints. Okay. So let me try to explain that further. So if you have a robot like this, right? Regardless, so I'm not going to draw the joints, only the end effector. So if you want the spatial velocity of your robot arm, your end effector, spatial velocity of the end effector to have Vx, Vy, Vz, omega x, omega y, and omega z, okay, so this depends on the application. If you want to use the end effector to pick and place an object in a 3-dimensional space in a various poses, then probably you need all 6 components, because you not only you have to move your end effector, you also need like certain orientations of the end effector. So you need all 6 components. Okay, 6 components. And if this is the case, you need to build or to have a 6 degree of freedom robot arm with 6 joints. Okay. On the other hand, let's so you can draw your own robot arm here, right? So on the other hand, if you have another scenario, this is the base of the robot arm, and you only want to use the robot arm to draw, right? Let's say this is a paintbrush, for example, right? For a weird reason, you want to use your robot arm to draw. And in this case, you can more or less think, right, logically. Probably you wouldn't require. So this is the end effector, right? This is the end effector of your robot arm. Probably you wouldn't require your paintbrush to be rotated. You only want to move it, right, in x, y, and z direction. So if this is the case, your spatial velocity only needs to have 3 components: Vx, Vy, and Vz. Probably, right? I'm saying probably. It depends on what kind of surface you want to paint or draw on. So if you have a flat surface only on the floor, this is the paint, the canvas that you want to draw on, right? Probably you only require the end effector, which is a paintbrush, to be only to move in only x, y, and z direction or motions. So if this is the case, you only need a robot arm which has 3 degree of freedom. Okay, so probably you need 1 joint here, joint number 1, joint number 2, and joint number 3. So a robot arm with 3 joints will be enough for a painting, drawing, or writing application. Okay, so that is the significance of this equation. All right. So the Jacobian matrix for a 2-link robot with the configuration pi over 4, this is 45 degrees perhaps, and minus pi over 2, this is 90 minus 90 degrees, shown in figure 4. This is figure 4. It's a 2-link robot arm where theta 1 is 45 degrees and theta 2 is minus 90 degrees. And the Jacobian is given by this. Okay. And to achieve end effector motion of 0.1 meter per second in the y direction, that means I want the end effector, this point here, to move this way, to move in this direction, positive y, right? We in this chapter we always refer to the world coordinate frame when it comes to the spatial velocity. So I want to achieve a spatial velocity of Vy equals to 0.1 meter per second. I want the end effector to move in this direction. Okay, 0.1 in the y direction. So we can use the inverse of Jacobian. You take the inverse of this, you multiply with the desired spatial velocity. So Vx equals to 0, Vy equals to 0.1 meter per second. And the computed joint velocity is 0.0707 radian per second. That is theta 1 dot, and theta 2 dot to be 0. And let's try to investigate if this is correct. So if I have theta 1 dot to be non-zero, right? Theta 1 is non-zero, right, in this direction. Why in this direction? Because if this is x, this is y, and z is pointing towards you, right? And so this is positive. Positive, if I have theta 1 dot to be positive, for example, 0.0707, and theta 2 dot to be 0, the end effector will indeed move in this direction at that instant, right? So in this configuration, if I have theta 1 dot to be non-zero and theta 2 dot to be 0, indeed my spatial velocity is 0.10. Sorry, 0.1. That means Vx, I have no motion in x direction, but I have motion in y direction. Okay? So, any questions so far? Do you understand so far? Any questions so far, guys? Hello?
No question, sir.
Okay. So what does it mean? What does it mean? How does our end effector move if I say that I want to achieve end effector motion of 0.1 meter per second in the y direction? What does it mean physically? How does the end effector move? Any idea?